The next topic is thin-walled pressure vessels, which is also the last topic for this module. Let's have, once again, a bit of an introduction. So the topic is thin-walled pressure vessels, and those vessels are usually in the form of a cylinder or a sphere. So a cylinder or spherical shell is considered to be thin, since the topic is thin-walled cylinder. So it's considered to be thin when the wall thickness T is less than or equal to D over 20, where D is the internal diameter of your vessel. Okay, so this is just a criteria to determine if your vessel is thin-walled. Don't worry though, all of our examples will be thin-walled, so we don't have to go through this criteria anymore. So generally, cylinders are employed for transporting or storing fluids, for example, liquids and gases. So you have your LPG cylinders, boilers, and storage tanks, etc. So because of this, it's filled with water. Therefore, your cylinders and your spherical shells or pressure vessels, from the name itself, will experience an internal pressure, okay, due to what it's storing. So these are examples. So this is may baliktad. May fix it. May baliktad. So spherical vessel, and then your spherical cylindrical vessel. Okay, so that's what it looks like. So you have an idea of its actual form when we're solving for problems like this. Okay, and then these are the following equations that we need to know or get familiar with. First is bursting force. It's essentially the force that is making your vessel feel like expanding or contracting, but usually it's expanding. So bursting force is outwards towards the surface of your cylinder or vessel. And the equation for that is PDL, okay? And then for the top and bottom caps for your bursting force, the equation is P times pi d squared over 4, okay? Where small p is the pressure, uniform pressure. Capital D is the diameter of your vessel, and then capital L is the length of your vessel. Obviously, this is not applicable for spherical, or rather, this equation is not applicable for spherical vessels, but this is. Okay? And then we have tangential stress, also known as circumferential stress, because that force, again, mostly causes your vessel to expand. Okay? That expansion creates stress along the material itself. Okay? And that stress is tangential, meaning it's also experiencing a tangential force, right? Just imagining stretching, the stress is along the perimeter of your vessel. So therefore, we also have tangential stress. And the equation for that is sigma t equals PD over 2t. And then finally, okay, if you have longitudinal stress, okay, not only is it expanding, it's also lengthening. Okay, so the sides of the walls of your vessel are lengthening. Because of this deformation, it's going to experience again stress. And we call that longitudinal stress because it's along the length of your cylinder, along the dimension L. And the equation is PD over 4T. Now, before we move on to the equations, I'd like to show you how these equations came to be. Let's start first with bursting force. As I've said earlier, bursting force starts from the center and then outwards. Okay. So therefore, we'll take a portion of your cylinder. Okay. For example, here. So that's a portion of your cylinder. Okay. And then this is the length, total length of your cylinder. So if it's standing, okay, that's your cylinder. We're just taking this portion, okay? So that is that. I just made it horizontal instead of vertical. And then from this, it's going to experience pressure, okay, which looks like this, okay? So that pressure is experienced by the surface area. Now, the equation for pressure is F over A, force over area. What we're concerned with is force, so force equals P over A. Now, before we do that, since the force being experienced by each segment is different, we're going to divide this into small strips and take the summation of that to get the total force, okay? So first, due to that pressure, okay, we have force being experienced by your cylinder, okay? And that force is radially outward. However, if you've noticed for this portion, if I keep drawing the free body diagram, all the forces horizontal will cancel out because there's always a left and then a right counterpart of that force, okay? So horizontal force cancels out, Fx equals 0. So now, we're only concerned with Fy, okay? Now, before we create an equation for Fy, let's create an equation for that area, since again, F is P times A, and we're using a differential area, okay? So differential area is just a very, very small portion of an area. So looking here, that's equal to this arc length S multiplied by the length of the cylinder, right? That's the area of this, so SL. However, recall from your math subjects, S, again, arc length is just equal to r theta. So combining that into our original equation, dA equals SL, or it's also equal to r theta L. In this case, since we're taking differential area, this is what we need, okay? So this is the the angle subtending your S, so that's d theta, okay? So this is the general equation, this is the specific equation. So now, how do we solve for Fy, okay? Once again, Fy comes from your force P, okay? So if you have a force P here, a pressure P, this is your pressure P, okay? Differential pressure. We need to take the vertical component of that. And recall, component method, to get the vertical component of a force, that's just force sine theta, okay? That's why here, it's P sine theta. Then multiplied by A, it's differential area A. And then, we're gonna take the summation of all the differential areas throughout this span. So that's why we're gonna integrate that from this point, 0, up to pi, since this is a circumference. Okay? That's why our integration is from 0 to pi. So now we have this basic equation for force, P sine theta dA from 0 to pi. Sub in our equation for dA, it's r d theta times L. So it becomes integral of P sine theta r d theta times L from 0 to pi. Now, radius is just diameter over 2, right? So this becomes d over 2. I just moved the variables around. So P times R, or P times d over 2, times L times sine theta times d theta. Okay? Now, take note, I mentioned earlier that the pressure being experienced by our vessels is uniform, meaning it's constant. And whenever we have a constant, we can just factor it out of our integral. So I'm going to factor P. Next, diameter of your pressure vessel is also the same, no matter where you take your area. So that is, again, constant. As well as length of your vessel, that's also constant. So therefore, I can just factor out PDL over 2. Okay? So I'm going to be left with PDL over 2 times integral of sine theta d theta. And recall from your integral calculus class, sine theta d theta is just negative cosine theta. And then evaluate that from 0 to pi. Okay? So I'm just going to factor out the negative to make things less complicated. So you get negative PDL over 2 times subbing in your pi and 0. So cosine pi minus cosine 0. Cosine pi is negative 1. Cosine 0 is positive 1. So negative 1 minus positive 1. Simplifying all of this, we get negative PDL over 2 times negative 2. 2 cancels out. And that's how we got the equation F equals PDL. Since again, Fx cancels out, so this Fy is also the total force being experienced by your vessel. Okay, F equals PBL. Now, another way to solve for this, and the easier way, or the easier way to get the equation, is by using projected area. Recall for bearing stress, we also use projected area. So same here with bursting force, we'll use projected area as well. Okay. So once again, we're taking half of your cylinder, okay, and then get the projected area. So this is the projected area of the bursting force here. Okay. So now the equation is F equals P times projected area. Okay. So F equals P. Again, our uniform pressure, and then projected area is just this, and that's equal to base times height, since it's just a rectangle. So that's L times D, or DL. So F equals PDL. Right? So that's a simpler way to find out that equation. And then, in a similar manner, okay, F equals P over A, for F equals PA, and now the area that we're looking for are the top and bottom covers of your cylinder. So since the pressure experienced here is not changing, we don't need to use integral calculus anymore. A is constant. Okay, and that A is the area of a circle. So pi over 4d squared, therefore FL to specify bursting force on the ends. Okay, that's P times pi over 4d squared. Okay, area of a circle. And so that is how you derive the equation for bursting force. Now let's move on to tangential stress. So sigma T, PD over 2T. So that's easy. Okay. So as mentioned earlier, the half of your cylinder will experience a force F, right? And then this force F will be countered by a reaction force along the material itself. So we'll call that P, because it's tensile, because it's elongating your cylinder. Okay? So we have P here and T here. We have a free body diagram. You can use your equilibrium equations to create an equation relating T and F. So summation of Fx equals 0. Therefore, you have 2T to the right, positive. F is to the left, therefore negative, equals 0. And then recall, okay, since this is creating a reaction force, it's going to undergo stress as well, specifically tensile stress. And recall from your MEC 30, equation for stress is just force over area. For tangential stress or tensile stress, P over A. Therefore, T is just tensile stress times area. Okay. And then F equals F. Recall F from our previous derivation, that's just PDL. Okay, L cancels out. So for sigma T is PD over 2T. Okay. Once again, T is just your resisting force for F. And then in the same way, we'll do that for the longitudinal stress again, but now the resisting portion is at the ends. So once again, this is experiencing a force F, right? This portion or material will resist that, okay? So in total, that resistance is this force T. So summation of forces equals 0, negative T plus FL equals 0, T equals FL. P is just stress times area. So stress is sigma L. Area is this, right? So perimeter times thickness of your vessel. So pi d for perimeter and then P for thickness and then equals, okay? We have an equation for FL, right? That's pi, P times pi d squared over 4. Canceling out pi and d, you get sigma L equals PD over 4T. Now look, comparing the two equations, right? We'll see that sigma T is actually twice the stress of sigma L, meaning sigma T will always, or tangential stress is always greater than longitudinal stress. Therefore, tangential stress or sigma T is more critical, meaning if we're checking for failure, this is what we need to use, or this is what we need to consider. Once again, that's your tangential stress. Okay? So those are the derivations for our equations. Okay? Next meeting, we'll have examples. Do you have any questions so far? None. Okay? So next meeting, Thursday, continuation of lecture, we'll have examples. And then on Saturday, you'll have your exam. I'll explain the exam more on Thursday as well. Right? Okay, it's almost time. Since you don't have any more questions, I'll dismiss you now. You may go. Bye, class.